I'm very excited to introduce today's speaker, Yejin Choi. I'm actually very super excited, and although I am sure Yejin actually doesn't need an introduction because most people in the audience follow her research very, very closely anyway. So Yejin is an associate professor at the University of Washington and also a senior research manager at AI2. She is a recipient of numerous awards, including ICCV Mark Prize, Borg Early Career Award. Her team won Alexa Challenge in 2017, and this year they got an Outstanding Paper Award at AAAI. But there are many, many awards, I'm sure, that I'm not listing. And to me personally, Yejin is always a gold standard researcher with research that is few steps ahead, bold, super creative, and fun to read. And I'm excited today we are going to see fresh from the oven, talk about, without further ado, Yejin will tell us what it is about.
Okay, yeah, thank you so much for having me here and joining this talk today. So the talk is somewhat brand new. I started giving this talk only about maybe 2 weeks ago. So it's motivated by the observation that we keep hearing human level or superhuman level performances on many leaderboards, but they're not very robust, the SOTA models, because if given either adversarial or out of domain samples, then something astonishingly silly comes out. So at this point, it looks like we know how to solve a data set without solving the underlying task reliably. So why would that be? Whenever we think about the fundamental differences between the way that human intelligence learns about the world representation versus how machines seems to learn primarily data set patterns specific in data sets, it's good to think about what about the human intelligence that's so different from AI, and see whether we can draw inspirations from human cognition. So when people think about that, oftentimes we talk about system 1 reasoning, system 2 reasoning, which became popularized due to this book, Thinking Fast and Slow by Daniel Kahneman. And it's good that we do think about this, but it looks like there's a bit of a myth floating around in the community that maybe we know how to do system 1 reasoning with the deep learning, and we only need to figure out system 2 reasoning. So in this talk, I'm going to dare say that this is just an incorrect way of understanding what we actually know how to do. So in his earlier work, Kahneman talked about the 3 cognitive systems that includes perception, which is sort of a separate thing compared to intuition, system 1, as well as a system 2 reasoning. So perception and intuition together correspond to this familiar system 1 type reasoning, such as automatic, fast, effortless, and associative. And then system 2 reasoning is the one that's slow and effortful. What's really quite interesting, especially for NLP people, is the fact that both the system 1 and system 2 reasonings require some sort of conceptual representations, reasoning about temporal causal relations across past, present, and future. And then also both of these involve language, natural language. And so when we think about different tasks corresponding to different cognitive systems, for system 2, people usually think about solving puzzles or writing programs or proving logic theorems. But the truth is, we invoke this for such intellectual activities as reviewing ACL papers or crafting ACL rebuttals. Well, hopefully, we hope that Reviewer 2 is invoking system 2 reasoning, not system 1 reasoning, who knows. The perceptual level cognitive tasks seem to correspond more to either object recognition or image segmentation or speech recognition. And in some sense, a lot of current NLP applications are formulated a little bit more close to as if it's a perceptual task as opposed to truly system 2 reasoning, in that language models, for example, is more about predicting which word comes next, which is fairly local and compared to system 2 reasoning. And then in between lies this intuitive reasoning, which corresponds to reasoning about preconditions, post-conditions, what happens before and after, reasoning about people's motivations and intents, their mental states and emotional states. So intuitive reasoning is what humans do at every moment, every waking moment in our lives without even thinking about it consciously. So this is a fairly reactive and subconscious inferences that we do. And then system 2 reasoning correspond to the sort of stuff that many humans might not even engage with for hours or even days. So this talk is going to be really about this thing in the middle, intuitive reasoning. To make my point a little bit clearer, let me use this example figure from Roger Shepard's Monsters in a Tunnel. In fact, the first time I saw this image example was at NACL 2015, when Fei Li, computer vision researcher at Stanford, gave an invited talk to keynote speech for visual intelligence. But when I saw this image, and then her making a point about this is not just about 2 monsters in a tunnel, but it's the sort of human understanding about this image includes inferences like 2 monsters are running as opposed to standing still on 1 foot. One is chasing the other as opposed to trying to copy his body movements. And then the chaser has hostile intentions and the chased is afraid, even though these 2 faces are actually identical. So what's happening here is that we hallucinate all these stories that may or may not actually be true, but we seem to strongly believe that these monsters are running, for example, as opposed to standing still on 1 foot. And there's really no reason to believe one is true, the other is not. But we tend to do this because we have certain expectations about how the world works. So this type of inferences are stochastic in nature. Anything is defeasible with additional context, but humans still do this all the time, and it's an important part of human cognition. And a great deal of intuitive inferences are common sense inferences that are the best described through natural language. And one thing that I would like to really highlight here is that this is no longer a categorical task across some predefined set of labels. We really need the full scope of natural language, not just the words. Words are not label. Words are just labels. They're not really natural language, nor graphs of words, like a parsing of these visual scenes into visual relations. So those are not enough. So the TLDR so far is that for intuitive reasoning, we might need to incorporate or consider language as the representation symbols. But when people say symbols, they oftentimes just think about words, but that may not be really enough. We might need to consider the full scope of language as the symbols. And if you buy that, then reasoning becomes generative tasks in the sense that, as opposed to discriminative, in the sense that when you're reasoning about or describing what's going on in this image, you're certainly not evaluating potentially like 1 million different sentences or phrases that might describe the situation and then score all of them, rank all of them, and choose which one is the most likely. That's not how we seem to reason. We seem to almost speak and reason at the same time on the fly, token by token, word by word. And so the space of reasoning in language is infinite, but we don't have to enumerate all of the possibilities because we have these capabilities of reasoning through generation. So that's going to be the focus of our this talk today, that reasoning, thinking about broad scope of reasoning through generation. And in the first part of the talk, I'm going to sweep through a set of unsupervised inference-time algorithms that aims to make lemonade from off-the-shelf neural language models, implying that language models are great, but there are some limitations. But if we add some algorithms, then better results might come out in terms of reasoning through generation. And then in part 2, I'm going to talk about something else, but let's begin with the first part. So this is our new paper to appear at EMNLP, which is about counterfactual and abductive reasoning. So let me introduce the task through an example. So imagine that Ray hung a tire on a rope to make his daughter a swing. And then sometime later, Ray ran to his daughter to make sure that she's okay. So as a human, we can reason about what happened in between, and then be able to say some hypothesis in natural language. And so, for example, maybe she hit the rope and the tire fell on top of her. So some sort of accident happened. And then counterfactual is another task that we aim to address through the same inference-time algorithm. So let me show you data set called time travel. So this is one example from that data set. Zach was throwing a party. All his friends were dressing up for this Halloween party, which is quite appropriate for today. And then thought about being a vampire or wizard, but decided to dress up like a skeleton in the end. But what if we introduce a counterfactual context to that? Perhaps this is not any Halloween party, but it's a Game of Thrones themed party. So if that's the case, then we need to modify or revise the story ending a little bit so that perhaps now it's more about a particular character like Stark or Lannister in that TV show, Game of Thrones. And ideally, we want to achieve this through minimal edit. So for humans, this is an easy task. Anybody can do this without having to train ourselves across tens of thousands of examples. We don't even need like 2 examples. So far, we looked at abductive reasoning and counterfactual reasoning. And although they may seem quite different tasks, there's one commonality, which is that both are types of non-monotonic reasoning that requires reasoning about the past context X and future context Z, or left context X and right context Z. And then we need to generate something in between, and this is a clear case of reasoning through generation. So let's think about what pre-trained language models might be able to do off the shelf. So first of all, we need the sort of neural language models that can generate at least a sentence, which means probably we want to use left to right language models like GPT-2 because there's no like general purpose neural language models that can do text infilling off the shelf. So if we do this, of course, these days, neural language models are quite powerful to generate what might come next, which is fairly reasonable, but it's not going to be able to incorporate this future context because it's not being conditioned on. So then what can we possibly do? Well, maybe you can try to concatenate both left and right context into the left context with some delimiter between the two. But of course, this is not going to lead to something reasonable because now this is not really following the normal temporal sequence of sentences. And you could try doing this through supervised, additional supervised training on top of pre-trained language models, but it's always going to be awkward because now we are really going against the original temporal sequence. So the question is there something we could do in order to somehow make use of pre-trained language models, but still be able to do this sort of reasoning? And as a matter of fact, humans are capable of doing this without fine-tuning ourselves on, thousands of examples, because we seem to have a particular kind of inference capabilities that allows us to think about both the past and future simultaneously and then generate what is missing in between. So in this work, I'm going to point out that, in fact, we could do this through backpropagation, and in fact, it has been used for image style transfer that we are familiar with. So given a style loss, we can backprop all the way down to the input image Y in order to convert that input to something else. And in doing so, backpropagation is used as an inference time algorithm instead of a training time algorithm. And during inference time, of course, we fix the model parameters and using backpropagation only for the purpose of reasoning about the output. So DeLorean is the name of the algorithm. I'm going to go through just a visual sketch of how the algorithm works, somewhat overlooking some technical details, but the intuition goes to something like this. So given the left context X, we do the usual left to right generation, but we only generate the continuous vectors corresponding to Y. So we are not really sampling real language just yet. So these are all vectors, intermediate representation. And using that, we can continue generate the given input, the future context Z. And in doing so, by doing so, we can compute the log loss of generating Z given X and Y. And once we have that, we can do backpropagation in order to update the intermediate representation of Y. And we can do this iteratively, combining forward and backward paths. And each time we interpolate the representation coming from the future and the representation coming from the past. After some iterations, now we can finally take the mixed representation in order to finally sample a sentence out. So this is how abductive reasoning works. And in fact, the two examples that I've shown you earlier are algorithm generated output Y. So counterfactual reasoning, although the task may have seem quite different, we can use a similar intuition, but using the loss function now being KL divergence between the original story ending versus the new story ending with minimal edit. So this earlier example about Zach considering Lannister, but finally deciding to dress like a Stark was model output, just coming off from pre-trained language models. So very briefly, here's the paper has a lot more detailed evaluation story, but the quick takeaway is that using DeLorean, unsupervised method based on human evaluation can do somewhat better than the supervised. So usually beating supervised method is hard. So although the delta difference may not seem too large, still this is a very promising result. And of course, all of these are much lower than human performance, which implies that although inference time algorithm might be able to draw the best out of neural language models, pre-trained neural language models, even without domain-specific, task-specific supervision, still there's a significant gap in terms of human reasoning capabilities and neural language models capability for very easy abductive common sense reasoning. Well, easy for humans, but harder for machines, of course. And then if we look at automatic evaluation, we do better than other unsupervised baselines, but do not beat the supervised baseline. But there's something important to note, which is that evaluation measures such as blue and rouge really give a lot more advantage to a model that learns dataset specific language patterns. So if we do everything completely off the shelf, then it's really difficult to know what sort of dataset specific n-gram patterns that we need to pick up. So by design, this automatic evaluation is not the most satisfactory method to use, which sort of motivates further research into automatic evaluation measures, better automatic evaluation measures for generative reasoning. And so here's another example of model output. Ray drove his car on a steep.
Eugene,
Yep.
we have a question in the chat.
Yep.
Actually, a couple questions. From Chirag, the question is, how is minimizing KL divergence any different from minimizing cross-entropy loss?
Oh, it's a little different in the sense that we are minimizing the KL between, actually the notation here is, I'm like overlooking some details, but notation here is a little bit confusing. But so Z correspond to original three, third sentence, fourth sentence, fifth sentence. And then they are both sort of like for counterfactual reasoning task, as we rewrite the story, they become intermediately, they temporarily, they become both Y and at the same time with a different sliding window. And so when we generate the output Y, we want to make sure that the task constraints for the data set is that let's not rewrite the story ending too different from the original story ending, but try to make the revision through minimal edit. And that way it's a little bit easier to evaluate because the output space is a little bit better constrained. So that's what we are trying to minimize here. I hope that clarifies.
Okay, would you like to take two more questions now?
Sure. Yep. Yep.
Okay, from Kundan, the question is, can you please elaborate a bit on the BERT metric that you used?
Yeah, I think it probably was a BERT score. Either that, it might have been, sorry. I think it may have been the next sentence prediction score that came off from BERT, but I will need to go back to the paper and clarify. The paper is online, so sorry.
Okay.
I just leave it at that.
And one more question from Maxine. Can you talk about how you conducted your human assessment?
So the human assessment, I mean, like due to the ambitious plan of the talk, I'm sorry that I'm not going into too much detail with any of this, but coherence means whether the middle sentence really addresses the partial evidences or context given by both left and right context. Sometimes people might say something like reasonable to follow after the left context, but something that does not really explain the right context Z. So that's exactly what we're looking at here. Some people might wonder, like, do we actually need to look at the language fluency as well? Usually the neural language models generate the fluent text if we just look at Y alone. So that seemed to be less of a concern so long as you start off from larger scale models such as GPT-2. Not sure if that answers everything, but. And I totally didn't talk about how we do human evaluation on counterfactual case. If time permits later, I might present extra slides, but for now, we might just move on.
Okay, go ahead.
Yeah. All right, so, okay, so we were here. So Ray drove his car on a steep mountain road and Ray was fine, but his car was totaled. So what happened in between? Probably some major accident, which is what the model generated. Another example here, Tara wanted to buy a new shirt for her upcoming school formal. And then the next second sentence, original second sentence was that she went to the mall with her mom. So she's going to a physical store. And then the original ending, third, fourth, fifth sentences are how they browsed the store for different options and so forth. So the counterfactual second sentence, on the other hand, is about online ordering. So she decided to order from online instead, in which case we shouldn't be talking about stores anymore. And indeed, the rewritten story ending now talks about just the shirt. Even now the third sentence changed to, they sent her a shirt that fit her perfectly, implying that the online store sent her the package. So Let's move to the second part, neurologic decoding as another example where inference-time algorithm might be helpful to better elicit reasoning capabilities from neural language models. So today, sequence to sequence is almost the dominant paradigm of training conditional language generation, including machine translation, dialogue generation, and image captioning, and so forth. There's something new called the common gen, which I'm going to use as a motivating example. So the task is something like this. Given a set of English words, generate something that's sensible, making use of all these words. So as a human, this is easy. We can do it without seeing even a single example. We can do this right away. But even if you train, even if you do fine-tuning or supervised training of a pre-trained language model across a lot of pairs of such examples, this is the model output, which forgets to incorporate 2 of the 5 words given. So another example is machine translation, where the recent work reported that oftentimes there's a gender bias kicking in, changing the gender of in the original sentence from she to he, of course. And usually as a human, we have grammar rules that we can incorporate in real-time translation, but this is something that neural networks are particularly worse at. Basically, we don't know how to incorporate symbolic rules in an efficient way. So in this work, we are trying to explore the possibilities of incorporating logical constraints, at least at the lexical level, in the inference time, and then see how much we can do by doing so. And there can be different situations in which being able to do that could be useful. So for example, if in a dialogue system response generation case, you might want to talk about Hilton Hotel for sure. You want to incorporate the address and phone number. So you could create logical constraints for the content that must be included. And then if you're generating a recipe, then you might be able to say, you might want to say something like, well, create some noodle chomen recipe, but make sure to use at least 1 type of proteins and 1 type of vegetables, but leave everything open-ended. So you might want to give logical constraints that can be translated to CNF form, conjunctive normal form, which is basically combinations of clauses, and each clauses contain literals. So within clauses, you can satisfy only one of the literal, 1 or more literals, and then you have to satisfy all the clauses. So in some sense, when we do this sampling during generation, we could convert these logical constraints into an additional term in the objective function to incorporate. So whenever we violate 1 of the clauses, now we have to pay for some penalty. And you'll be surprised how a simple idea of augmenting beam search algorithm with multiple buckets that correspond to different clauses can lead to much better results. So I'm not going to go into the algorithmic details. The paper provides much more details, but here's a high-level intuition of what happens through some examples. So this is a supervised model that still makes logical mistakes. And if provided with neurologic decoding during the inference time, on the other hand, now it can generate everything quite nicely. So we were curious, what about just a pre-trained language model without supervision? So without supervision, of course, off-the-shelf language models do not know what to do with any of this. So input doesn't make any sense. Output is going to be something entirely different. That's reasonable. So if we, which also says something about how supervised method, at least were able to incorporate the 3 out of 5 words on average. So they're learning some patterns implicitly, it's just not doing it quite correctly. But it turns out if we incorporate neurologic decoding, then even off the shelf, the generation looks great. And so the paper has a lot more empirical stories across the different data sets, but I'll be brief here just to highlight that, first of all, unsupervised neurologic outperforms supervised approaches without neurologic, but either beam search or some other sampling techniques that people often use. And so here we see that beam search is blue, that's a supervised, and then neurologic, supervised, and zero shot are green and yellow. And this is the higher the better. Coverage shows the percentage of the problems where constraints were satisfied. So this is the percentage of the problems in which all the constraints are satisfied. And of course, Neurologic will have a higher coverage, but what's quite surprising perhaps is the fact that even rouge and meteor of generation quality improves dramatically. In addition to that, now x-axis here shows the model size. So to our big surprise, unsupervised neurologic on smaller networks even outperform supervised approaches on larger networks. So this is sort of going against this recent trend, which has been that larger networks almost always work better than smaller networks, but perhaps that's true for seq-to-seq models with traditional beam search. But if we incorporate a little bit more algorithmic operations during the inference time, we might be able to do certain types of tasks quite well, even without supervision, even without using very large networks. So here, this unsupervised method, which is yellow on a smaller model, using smaller model, already outperforms supervised on a larger network. So yet another similar story is reflective decoding. So this is unsupervised paraphrasing and abductive reasoning. You might wonder, why is it that one algorithm for such a different task? But let me start with the paraphrasing. So this is intuition, which is that we're going to use left to right language models in order to generate what might happen next, but sample multiple possible next sentences. So that's our contextualization step. And then we trained right to left language model. So this model always reads the text backward. And using that, conditioning on the context, we can generate what might have happened in the past, which happens to be paraphrase of the previous, the input sentence. So here's one example, like what do people think of Americans? As an American, perhaps I'm not qualified to answer this question, or people have mixed feelings and so forth. So there may be different contexts. Together, this is sort of like a set of context that represents roughly the meaning of the input context. So this is sort of like a distributional hypothesis that's being used for inference time algorithms for paraphrasing. And so during reflection step, we're reasoning about which sentence might best deal with this set of context sentences. So let me just change the sentences into particular symbol S, and then S hat, and then CI. So roughly speaking, roughly speaking, what we're trying to do is, given a source paraphrase, source sentence to paraphrase as a source, we might be generating some context, and then the paraphrase of the source as head should be the kind of a phrase or sentence that would minimize the KL divergence between the left to right language model score, conditioning on the source, either the paraphrase, the source, or the original source. And in order to do that, we use left to right in order to generate some context. And then each context might have a different quality or weight for explaining the input as. So we're going to learn the weight for each context. and then take the product of expert using right to left language model in order to generate the paraphrase sentence. And in fact, there's really no reason why we should be doing this in only one direction. In reality, we do this in both directions so that we generate both left-hand side context as well as right-hand side context, and then mix the two. Now, about the abductive generation that we saw earlier through DeLorean, in fact, we can do this through reflective decoding as well. So what we really wanted to do is to be able to generate some intermediate sentence H between observation 1 and observation 2. And in order to do that, we can first generate left and right context, and then come back to the middle, which best describes what's missing. So I'm going to be super brief about the evaluation again, but here's the takeaway message. So in terms of SARI and human evaluation, ours work better than even the supervised best baseline, which was based on BART. So BART is a very powerful supervised method for paraphrasing at the moment. And we do better than that, except for BLUE. The important thing about BLUE, though, is that BLUE can be gamed by not paraphrasing at all. It turns out if you just copy and paste the original input sentence as is, then you can do really well on BLUE. So SARI is the new measure that tries to address that problem by incorporating novelty. And it turns out our method, especially because it's off-the-shelf language model without even fine-tuning on the target paraphrase data set, it just doesn't know the style of language that might appear in the gold paraphrases. But as a result, novelty can be stronger. So that's our evaluation story. And so up until here, we've looked at 3 different types of inference-time algorithms. And there's some interesting high-level perspective coming out of this set, which is that the first one is neural inference, in a way, neural backpropagation. The second one is classical search, that's a discrete. And then the third one is somewhere in between, in that it's looking at a set of samples that are discrete, but they're represented in a neural space through this distributional hypothesis. And in doing so, we are also making use of imagined context instead of the real context. And together, perhaps we didn't explore all the possible inference-time algorithms, but one speculative thought that I wanted to share with you is this idea that perhaps we really underexplored inference-time algorithms that can really draw the best out of off-the-shelf neural language models, because in especially recent years, there have been a lot of focus rather on scaling things up and scaling up the data set, scaling up the model, scaling up everything. But it might be that we can go back to algorithms and really develop algorithms, but we might need to really develop new algorithms that are better customized for neural models. Now, although I think algorithm can get us quite far, I don't think that's going to be enough in the long term. So the next part will be about that. But let me first complain about the current paradigm of learning based on multiple choice questions. So right now, this is sort of like the dominant paradigm. Whenever you have a task that you want to solve, just create a lot of QA problems with multiple choice questions, one of which is guaranteed to be a correct answer and something amazing should happen. But there have been these emerging concerns that neural networks learn or latch on spurious correlations in the data set, because even as a human, whenever we take exams that have a multiple choice question, sometimes we can answer some of these questions correctly based on exam writers' biases that kick in to the while crafting multiple choice questions. So we're not really truly estimating the AI capabilities. The other problem, though, practically speaking, is that in real life scenarios, usually nobody will give us there's no oracle that will provide us with the 4 magical choices to choose from, and one of them is guaranteed to be true. In real life scenarios, we might actually have to generate options on our own. So these multiple choice questions are really incorrect way of thinking about even the real life situations. Discrimination is not enough. We have to be able to generate the answers. The other thing to think about is the following, like imagine learning as a human about deep learning. And so we take a class, but imagine a professor who teaches nothing, but just giving you lots of exam problems, multiple choice questions with the correct answer. Even as a human, I don't think any human being can actually learn anything out of that based on just multiple choice questions, no lecture, no tutorial, no textbook. So that's sort of going against the supervised learning based on QA data sets. But then some might wonder, oh, wait a minute, self-supervised learning works really well. So imagine providing students with lots of deep learning code, a ton of it, and they have to read a lot of code and figure some. You can imagine that, well, that's not the most efficient way of learning. You might still figure something out on your own. But imagine the program language is not even Python. It's written in completely new language that you've never seen before. It's all written in Korean, in fact. Can you really learn anything as a human? I think not. So the current paradigm of learning, either based purely on self-supervised learning, on predicting which word comes next or which word is missing in between, combined with this lots of multiple choice questions, I think there's something really wrong or limiting about the way that current paradigms are set. So what I'm going to explore next is, can we teach machines concepts more directly? And probably this is a big research question for which I don't have a very good answer for, but I would like to at least explore learning from declarative knowledge. And for that, I'm going to talk about first common sense knowledge learned from declarative knowledge graphs. And then next I'm going to talk about social, ethical, moral norms. So this is our new paper on symbolic and neural common sense knowledge graphs. And in fact, this builds on our previous work, Atomic and Comet, which correspond to symbolic knowledge graph and neural common sense transformers. And as we see that people start using it for some downstream applications, we got excited. So we decided to improve it further. And just in case you're not familiar with Atomic, the original one, so this is a small subset of atomic knowledge graph, which might have things like because someone wanted to do something, so this is intent. As a result, someone might want to do something next. Sort of like preconditions before taking an action. So there were a lot of this social common sense knowledge incorporated in the original atomic knowledge graph. And we decided to strengthen that with the physical entity common sense knowledge, such as money can be used for paying repairs, but we also have a fun additional knowledge, such as, what can you do that's not stereotypical, like folding into origami. I don't think I've ever done that before, but I believe that's possible. We also have new knowledge that's about more event-centered, and that can reason about, if you want to get your car repaired, but what sort of situation might make that impossible? Well, if the car is totaled, then you cannot get your car repaired. This graph is fairly large, and it contains a lot of natural language inferences that amounts to 1.3 if-then rules, or rules of thumbs that people have about how the world works across 23 common sense inference types. The paper provides a lot of evaluations comparing different knowledge graphs and so forth, but here let me just highlight one thing, which is comparison against the GPT-3, because this is sort of like what everybody is curious these days. So here's our new Comet 2020 built on top of BART. Compared to that, GPT-3 doesn't even fit into the slide because it's more than 400 times bigger than BART. And with that in mind, GPT-3 is doing quite well. So this is a human evaluation on machine-generated common sense prediction given some context, provided there's one node, one edge, and then you have to generate which other node might come next. And in this setup, our evaluation is set up adversarially for COMET in the sense that our knowledge graph is split into training and test, such that test set is as different as possible from training set, because we didn't want to just test retrieval quality. We wanted to see how the model can generalize and then reason well on previously unseen events, because common sense, space of a common sense is so large, there's no way we can encode everything into symbolic knowledge graph. I'm pretty sure that 1.3 million rules are not enough. Even 10 millions probably will not be enough. So we need a model that can generalize and reason about previously unseen events. So of course, GPT-3 is based on few shot. GPT-2 is based on 0 shot. So few shot has that advantage, but still the jump from GPT-2 to GPT-3, this is quite remarkable. And it's quite impressive how much larger scale models can achieve without supervised learning. But even if GPT-3 is available freely, which it is not, but we cannot even download it. It no longer fits into anybody's machine anymore. So in this regard, BART is really nice because it's small, and instead of burning the planet with a lot of GPU compute, we created jobs for humans to do talking. So I think there's some interesting takeaway message from this, which is that maybe we need to think more about teaching computers with a declarative knowledge. And in some sense, this is like a textbook for machines to learn about how the world works. So here's the demo page. It's still based on previous COMET. But one thing to point out is that it turns out COMET generalized much better on out-of-domain samples than we realized during the time we were publishing our paper. So here's some fun examples. Sanya rides into the sunset or a motorcycle after solving AI. This is a snippet of the online demo output. So this is a little bit out of domain in that I don't think the solving AI is part of original atomic graph. And in this case, the prediction is really focusing on how she might be having fun. She needed to buy a motorcycle before, and she might be seen as someone daring, brave, adventurous, and reckless. Still, it's not broken entirely or anything. The prediction is pretty reasonable. Gary breaks the world record for most controversial tweet. So tweet is not part of atomic, and atomic, by the way, doesn't even have people's names. So it's not going to learn particular Gary in the world. It's only going to know that this is some person name. So the prediction is that maybe he wanted to be famous. He probably needed to do some research, write a book, magazine article, blog post. He might be seen as a famous, and he might feel proud afterwards, celebrate, tell everyone about it, and so forth. So the predictions are pretty reasonable, and this comes from the fact that our COMET model is trained on atomic knowledge graph after pre-trained on a lot of raw text. So it's a transfer learning from language to knowledge. Gary Marcus, as we know, is not very happy about current deep learning models, because if he gives a context like what happens when you stack kindling and logs in a fireplace and then drop some matches, is that you typically start A. And then GPT-2 continued his prompt with some nonsense. So he has a deep concern about the future of deep learning. But one thing to note is that, well, language models are language models, not knowledge models. So if you try COMET, which is knowledge model, and I give this prompt, Gary stacks kindling and logs and drops some matches, then you get correct prediction. And this is, again, surprising in that atomic events do not have this sort of like conjunctive constructions, and stacking kindling and logs do not appear in atomic knowledge graph, but it's able to generalize to reason about previously unseen event quite nicely. So the takeaway message here is that language models learn implicit knowledge or observed knowledge through self-supervision. Atomic is a symbolic knowledge graph written in natural language that allows us to learn from declarative knowledge. And in fact, this is how children learn about the world as well. They don't just read a lot of New York Times articles and watch a lot of YouTube videos. They ask questions to their caregivers, why something is this, why something is that. And in some sense, the conversation that happens in early childhood is a little bit like the sort of obvious things that's written down in atomic knowledge graph. Atomic in particular focuses on causes and effects, causal knowledge, sort of viewing a lot of reasoning, causal reasoning as sort of like inferential patterns that we store as common sense knowledge. And then at the end of the day, though, everything becomes neuralized models, because that seems to be what really generalizes well to computational and previously unseen events. Now, finally, let me highlight the Social Chemistry 101. This is our new paper at EMNLP. And in order to motivate that, let's see how much GPT-3 might have already solved the morality question. So first, I gave this context a few days ago. Running a blender at 5 a.m. is rude because it says, because you can wake up the entire neighborhood. What kind of blender is that? You can only do it though if you're making a thick smoothie and need to incorporate some ice. So that's a very confused way of thinking about whether it's okay to run a blender in the morning or not. But I was curious to give something a little bit dangerous, like it is okay to post the fake news if ... And then GPT-3 says if it's in the interest of the people. So I was thinking, oh, this is not very good. So let's try again. And then it says something even worse. So the story here is that we do need to teach AI with people's descriptive knowledge, descriptive ethical knowledge, given in the declarative form, because brute force large networks, no matter how much data you feed, will not be able to figure everything out on its own. And in doing so, we really need the full scope of language. This is no longer amenable to just some categories to choose from. Let me give you a concrete example to show how the complexity of what we are dealing with. So asking my boyfriend to stop being friends with his ex. So this is a concrete situation. And then we can think about a variety of different rules of thumbs. So maybe it's okay to ask your significant other to stop doing something that you're uncomfortable with. But maybe another viewpoint could be that, well, it's not right to tell someone else what to do. Or, you might, have another counter argument to that, well, you should make sure that SO doesn't feel like they're the lower priority. And, depending on which one you support, you're sort of emphasizing different aspects of moral dimensions. So either you're emphasizing on authority or loyalty or care, and also some of these are really about different characters or people in the scene. So different rules of thumbs attached to or are grounded to different people in the scene. So for any given one situation and one rule of thumb, given in natural language, we created this structured annotations that I'm not going to go into the details of, but part of this annotation is motivated by the moral foundation theory of Jonathan Haidt. And in total, we have 300,000 of rules of thumbs grounded on 100,000 of real life situations that we crawled from internet. This is real life situations that people do talk about and discuss as morally ambiguous or controversial situations. And then some of these correspond to cultural pressure, some of these correspond to legality and so forth. So the paper provides the standard, tables with lots of numbers, but let me just highlight the high level ideas here, which is that when we think about cultural norms or social norms or moral norms and ethical norms, these things are not easy to completely segregate them out. They're sort of overlapping. They're different, but they're sort of overlapping. And there's some like fundamental questions about who decides what's the right thing to do. And the direction we decided to take is descriptive norms or descriptive ethics, which is a line of research in ethics that ask people what they think about concrete situations. So this is where natural language becomes really relevant, of course. The entirely different direction that people might be familiar with is prescriptive norms or ethics, which concerns more about what are the fundamental 5 values that you must, value no matter what. Maybe, it has to be about caring, I don't know. But there could be 5, there could be 7, there could be 10. Who decides how many, and who decides which are the fundamental dimensions that one must abide by? So prescriptive norms focus more on that. But the problem with the prescriptive norms in terms of actually making computational models is that it's not going to be useful for AI to do anything with it, because still we need to teach how that sort of like major values align with particular grounded situations. So the way that we need to explore this space is through just natural language, really asking people what they think. And this is where I think NLP field has significant chances of making contributions to computational ethics. So I'm going to now wrap up the talk. So common sense AI, when searching this word from ACL Anthology, I think I probably presented this particular page 3 years ago at CMU, but there's a void. So when thinking about common sense, several years ago, I was told not to work on it because nobody will take me seriously then. But sometimes you feel like you want to be rebellious. So I decided to go ahead and still do it. But it was in part because of this realization that although a lot of smart people worked on common sense in the past, the failures are inconclusive because it was based on weak computing power, not much data, no crowdsourcing platform, not as strong computational models like transformers. And the real problem there is that they chose wrong conceptualization or representation forms, which were based on logical forms. I don't think we can go that far through that. I think natural language is the way to go. So I don't actually know how to really get there though, but one thing for sure, brute force larger networks with deeper layers will not do it, in the sense that we cannot reach to the moon by making the tallest building in the world 1 inch taller at a time. So in this talk, I presented alternative path to common sense in part by unsupervised algorithms, and then in the other direction through declarative knowledge and knowledge modeling. And more details on common sense, recent common sense work can be found in this tutorial available online, in which I'm like not teaching very much. It's mostly the other speakers, amazing speakers doing the work. Let me wrap up the talk finally with one last slide about language and reason. So for some reason over the past year, I started reading non-computer science books, and this one is really good, The Enigma of Reason, which talks about sort of like system 1 and system 2 reasoning. And so intuitive inferences, the book says, is a great deal about extraction of new information from the information already available. So it's like a common sense reasoning, abductive reasoning, and counterfactual reasoning, where you generate new information that's not necessarily precisely entailed by the context, but likely to be true. That's what new information means here. And then reasoning, so system 2 reasoning, in our mind oftentimes are not really used in order to make important decisions. So not to guide oneself means making an important decision, but to justify ourselves in the eyes of other people, or to convince other people of our decision that we already made. So for example, when I believe that language is the way to go, this is true that I feel like I just made the more intuitive decision, But now that I have to give a talk, I'm trying to think hard how to convince myself to other people. And so this book is quite fascinating in that it really goes one step further to say that reasoning really solves the system two. Reasoning solves the purpose of communication. And the separation between this system one and system two is not that clean cut, in that even system two reasoning seems to build on a mechanism of intuitive inferences. In any case, the conventional mathematical logic plays at best a marginal role, which is also investigated deeper in this book by Philip Johnson Laird. I think he might be better known for mental models, but his newer book, How We Reason, is really very nice in this regard. So I'll stop here and thank you.